probably get going. Adnan, are you ready? Then I'll just make a super short introduction.
I'm ready.
Yeah, so we're not very formal. We're thinking of this. If this were a Simon's workshop, you'd have all of these wonderful talks just in sequence. Now we're spacing them out one a week, but just by a way of very brief introductions, this is the Beyond SAT workshop. In the context of SAT, I mean, it could be mentioned. I guess the two contexts in which Adnan would be cited is for that he showed that in fact conflict-driven closed learning solvers have the potential to be as strong as general resolution, a question that had been open for quite a while. I think it's also fair to say that he is behind one of the popular heuristics that is these days more or less established in SAT solving, namely phase saving. I think that's correct. But of course, Adnan's main claim to fame, and I'll try to keep this short, but it goes far beyond SAT, even beyond NP. And in some sense, Adnan was even, before we dreamt up this Beyond SAT program, Adnan was pitching Beyond NP and organizing Beyond NP workshops, so giving inspirations to us. And I think what we might be hearing about today is knowledge compilation and representation in some sense, maybe, but I won't guess. I will leave the floor to Adnan, and he will tell us what he will talk about.
Very good. Thank you, Jacob. All right. So the title Beyond NP with Tractable Circuits, and the idea is we're going to try to target problems that are beyond NP, but in a systematic fashion using the theory of tractable circuits. So let me start with this slide, which actually sums up a lot of what we'll be talking about today. So what we have here is complexity classes. Okay, so we know NP, and there are classes that are beyond that. Some are familiar. PP now is pretty popular. That's the counting class, and there are other classes, and we're interested in solving problems in those classes. If you look, for example, at probabilistic reasoning and machine learning, I'm showing here a picture of what's known as a Bayesian network. There are 4 classical or canonical problems on these that people have been working on for decades, and each one of these 4 happen to be complete for one of these classes. We're going to take a look at that. Now, the interesting thing is, if you look at these classes, the prototypical problem for these classes, complete and represent these classes, are all on Boolean formula. And also, there is now efficient, very practical reductions that can take some of these problems that I mentioned here, the 4 canonical, and write out Boolean formulas that correspond to these problems. So we can solve these now systematically by solving the prototypical problems for these classes, which are all problems, as I said, on Boolean formula. We're going to take a look at these in just a little bit. Now, the question is, then how do we solve these problems? How do we solve these prototypical problems for these classes, which, as I mentioned, are all questions on Boolean formulas? And the bulk of the discussion today is that we can do this systematically by compiling the Boolean formula to a tractable Boolean circuit. So what is a tractable Boolean circuit? It's just a Boolean circuit in the classical sense with some additional properties on it. And as we add properties to these circuits, they start attaining names. They become distinct creatures. And as you'll see, for example, as part of the theory of tractable circuits, we do know for each one of these classes, we do know of a circuit class or a property that if you put on a Boolean circuit, which allows you to solve that problem in time linear in the circuit size. So what that means is you give me a Boolean formula that corresponds to one of these problems. You want to solve it. If I manage to compile it into a tractable circuit of an appropriate type, then I'm done pretty much, because I can then solve the problem by polynomial time on this guy, typically linear, as you would see. So from a practical point of view, you give me a problem in this class, let's say one of these guys here, I write out a Boolean formula through a reduction, and then I compile this Boolean formula into a circuit of a tractable type, and I'm basically done. So we're going to be talking about, in just a little bit, about the 4 prototypical problems for these. We're going to spend most of the time talking about tractable circuits, the properties, and all of that. I'm going to show you a core reduction later, which is behind a lot of reductions that happened later. It's pretty simple, pretty intuitive to bridge those two worlds of numeric and symbolic. And we'll also, towards the end, talk about the compilation process. Now, in connection to tractable Boolean circuits, there is this story about tractable arithmetic circuits. And as you'd see, there's two tales or two ways to describe arithmetic circuits. One of them will be as a side effect of the first story. So when I have a tractable Boolean circuit like this one, you can do two things with it. What you would probably expect, which is purely symbolic manipulations, but you can also do numeric computations based on this Boolean circuit. Roughly, it would take the form, instead of passing Boolean values, zeros and ones to the circuit, I can start passing numbers. And then what does that mean? Well, we'll end up multiplying at AND nodes and adding at OR nodes. So we end up synthesizing an arithmetic circuit that's doing that computation. Now, this part of the story will emerge as we're doing the Boolean tractable circuit story. But what happened is, as you'll see, these type of arithmetic circuits were picked up big time in machine learning and probabilistic reasoning. And while the story that we'll hear initially is purely computational, that I'm using this as a computational device. For example, one of the pictures that will emerge as we go on, you'll see that you take a probabilistic graphical model like a Bayesian network and effectively synthesize an arithmetic circuit that allows you to do computations on that probabilistic model in linear time on the circuit size. So that's the story, the computational story. But what people started doing is they started handcrafting these arithmetic circuits and even learning them from data. So bypassing the notion of a model that I'm trying to do computations on. And that demanded an independent treatment that's different from the one that I'm going to be giving you initially. So we're going to get to that later. Now, this is the agenda. It looks big, but some of these elements are pretty short. I'm going to just start with a couple of words on complexity classes, basically the prototypical problems for these classes that we mentioned. Most of the time will be spent on tractable Boolean circuits, because really that's the essence of a lot of what's going on. As I promised, I'll show you the core reduction that bridges the two worlds of probabilistic and numeric. And then we'll talk about tractable arithmetic circuits, knowledge compilers, a word on explainable AI. Again, that seems like a lot. We'll see how much we'll finish, but some of these components are pretty brief. Now, let's start here so that we're all on the same page as far as at least what are the four classes of problems we're trying to solve here. So I'm going to illustrate these, even though they're typically done on Boolean formulas. I'm going to show them on Boolean circuits just because it's pictorially more appealing. So we have a circuit like this with four inputs on and off. And as we know, the simplest problem is SAT, right? So is there a circuit input under which this circuit will generate a one output? We know this is SAT, it's NP complete. Now, the second class, the problem is, I'm now going to ask you if the majority of circuit inputs satisfy the circuit, right? So there's 16 possible circuit inputs in this case, and is 9 or more of them will satisfy the formula. As we know, that is MASH SAT, right? And that's the prototypical problem for the class PP. And the next two classes actually require that we divide the inputs of the circuit. So you have to pick some partitioning of the inputs. In this case, let's say Y and Z. And here they are. And the first one says, can you fix the Y inputs? Is there a setting for this under which the majority of Z inputs are satisfying, all right? And that is EMASH SAT, that's NP to the PP. And you can probably guess what the last one is, right? The last one, so this is there an instantiation of this under which the majority of that? The next one would be, are the majority of Y inputs such that under each one of them, the majority of Z inputs satisfy? And that ends up being MASH SAT, and that's PP to the PP. Now, as I said, of course, everybody's very familiar with SAT. This is becoming quite familiar these days. These are pretty actually important, and maybe you'll get a sense of them when I show you in a little bit the problems in probabilistic reasoning and machine learning that are kind of prototypical for these classes. But before I move on, I want to mention two variants on MASH SAT, because those are very important practically. So these are all decision problems. And what we're going to see in the reductions, we'll be talking about functional problems. So Okay, these are the four probabilistic reasoning problems. We're going to look at them shortly. For MASHSAT, is the majority of inputs such that, are there a majority of inputs that satisfy the circuit? You can actually count those, right? And that's known as sharp-SAT or model counting. I want to count. I want a number, not just a yes/no answer. But even more importantly, from a practical point of view, is the weighted model counting version of sharp-SAT. So in this situation, what I'll do is I will assign weights to every variable setting. So if x is 0, that's a number, a weight, a positive number. If it is 1, that's another number greater than or equal to 0, and so on. And now when you have weights for these literals, then you can assign a weight for an input to the circuit. And we do that by multiplying the weights of the corresponding variable settings, all right? And now I can tell you, okay, I want the weighted count of the circuit's input that generate a 1, and that's known as weighted model counting, or WMC, right? So I don't assign a value of 1 for each satisfying input, but there is a weight. And that's the one that actually gets used quite a bit in practice. And it is important enough that I'm going to visualize it differently. So instead of a circuit, I have a Boolean formula now. And these are the three variables, and these are the different settings of these variables, and I have a weight attached to each one of these guys. And then I'm asking you to sum the weights of the satisfying assignment. And it's important to realize here that these weights are induced by literal weights, right? Otherwise, I would need an exponential number to specify the problem. No, in this case, I need just a linear number of parameters, these literal weights. So a weight for A, a weight for not A, and you'll see that later how it plays a role in the reductions. Very good. So these are the problems we're going to be looking at, or these are the prototypical problems for these classes. And let me just quickly just give you a sense of what these guys are. See how interesting. Again, you're familiar probably with these. Maybe these are not as familiar. And these three queries, MPE, MAR, and MAP, have been around for decades. I think they're all in Yuda Pearl's book from the 80s. This one is pretty recent, from about 10 years ago. Let's take a quick look, just so that we have a sense of what we're going to use tractable circuits for. Bayesian network, as you know, is a graphical model. It specifies a probability distribution. And one query is, in this case, we have a condition. We have two tests that bear on that condition. One of the tests depend on the gender of the patient. And this is just a hypothetical notice saying whether the two tests came out the same. I'm not showing you the whole Bayesian network, but one of the questions you can ask is, you come and say someone did the two tests and they agreed. They came out the same. I'm not telling you how they came out, but they came out the same, either both positive or both negative. And you're trying to find the most likely state of the variables under that evidence. All right. So you find the most likely state of the variables. And that's called an MPE, or a most probable explanation, MPE. And here you see the answer. C being no, sex female, both negative, that's the most likely state of that. So the decision version of this is there an instantiation whose probability is greater than some threshold that is actually NP complete. And the next one is the PP complete version, which is known as MAR, and computing marginal probabilities. That's kind of the more classical query. Just compute the probability. I give you the fact that this guy came out positive, this is negative. What is the probability that the person is a male? Okay, computing that probability. Again, the decision version of this is PP complete. And the next one, going up the hierarchy, the map. Map is actually very similar to MPE, except I'm optimizing over a subset of the variables. So I want the most likely state of a set of variables given some evidence, but you get to choose those variables. It's not all of them. And interestingly enough, while optimizing over all variables is NP complete, this guy ends up being NP to the PP complete. This is harder if you get to choose the variables and optimize the subset of the original ones. As I said, these three have been around for a very long time, bread and butter. They underlie a lot of things that goes on. The next query is relatively recent, about 10 years ago.
Adnan, just a question on your previous slide. So if you go back, what's the input that I get? I get that the red thing is the outcome, and you also told me the blue guys that you're interested in.
No, you give me the Bayesian network.
Uh-huh.
You give me the evidence that I know that they agree that the two states came out, and you choose the variables that you want to optimize over.
Yeah.
These two guys. And what I give you back is this. I give you back C is no and sex is male. That's the output.
Okay.
So I'm telling you this is the most likely state or a most likely state of these two variables under this particular evidence.
Got it. Thank you.
All right. Very good. You know, sometimes people in engineering, they call it state estimation. And this is partial state estimation. MPE is full state estimation. Very good. Now, the next one is pretty interesting. Now, and it's been actually receiving quite a bit of attention recently. You know, if you look at these Bayesian networks, they're usually used as classifiers. So this is a Bayesian network where I have 3 tests, urine, blood scanning, and I'm trying to detect whether someone is pregnant or not based on these results. So typically you compute the posterior on pregnancy and check against threshold, and then you get a yes, no, pregnant, not pregnant. So in this case, let's say the threshold is 90%, and all you know is that the scanning test came out negative. So the probability of pregnancy is 40%, that's below the threshold, the decision is no. Okay, now, what is the query? The query, again, you pick up a set of variables. In this case, we pick up urine and blood. You pick them up as a user, and you tell me, what is the probability that my decision will stick even after I observe these two variables? And in this case, the SDP same decision probability is 78.7%. That is. Right, now the decision is no, not pregnant, given this. And what I'm telling you is if you were to observe these variables, the probability that your decision will stay the same is 78.7%. So it's kind of an expectation. SDP is an expectation. And you can imagine how practical this is, because I can use this to tell, is it worth getting some information or not? What's the value of information that I can get from a certain sensor, and the decision version of this PP to the PP complete. And interestingly enough, as I said, all of these problems now that I showed you can be solved by taking the Bayesian network, writing out a Boolean formula. I'm going to show you how later. Compiling that Boolean formula to a Boolean circuit of an appropriate type. And if you succeed, so the only bottleneck from a computational point of view is that compilation. If you succeed in the compilation, then you can solve these problems in linear time, on the size of the final tractable circuit that you got. Okay, so it's pretty exciting. Well, let's see what these guys are. You know, these are intricate problem, rich complexity classes, and what you'll see is for each one of them, pretty much we know of a property on Boolean circuits that unlocks those classes and those problems. So the story of tractable Boolean circuit that we'll be painting can be summarized in a picture that looks like this. So we have a Boolean circuit. We're going to start with a basic type. It's called NNF circuits. I'm going to show you this next. And then we're going to start adding properties. These are example properties. These are not exhaustive, and we're not going to go over all of these. But when you add properties on these NNF circuits, you start getting different circuit types. Some of them are familiar. These are very familiar. And some of them are probably less familiar. And in fact, this is the weakest type here. And as you go up here, okay, except for this here. The more properties you add, two things happen. You get more computational power, more queries become polynomial time on the circuit, but then the circuit size gets larger, right? So there is this study of 3 dimensions. What are the properties? What do they enable in terms of computation, and what happens to the circuit sizes? That study happens now in AI under the label of the knowledge compilation map. So there is this notion of tractable circuits and knowledge compilation. And let me say a word here, it's important. In AI, traditionally, knowledge compilation has not been tied to the notion of tractable circuits. Knowledge compilation was just about, you give me a Boolean formula, I want to answer something, let me compile it into something that facilitates that computation. But as of about 2 decades ago, starting with this paper, there was a systematic picture about compiling into tractable circuits that we'll describe next that has been evolving over the last 2 decades. And then there was a stronger connection between knowledge compilation and tractable circuits. So most of what's happening today on knowledge compilation is about compiling Boolean formulas into tractable circuits, all right? The word knowledge compilation is somewhat broader though. Sometimes you'll hear me talk about this as knowledge compilation, sometimes tractable circuits, and I hope you understand what's going on. Knowledge compilation map is the title of this paper, which provided the first picture of the type that I'm going to be mentioning next. Okay, let's move on.
Question?
Yes.
So when we say that these are polytime, then you mean that that's polynomial time in the size of the final compiled circuit?
Exactly. And
okay.
Of course, you may not succeed in getting that circuit. That's actually what you'll see next is how simple this whole formalization is. Really pretty intuitive and simple, but the real bottleneck is the compilation. And that's one of the values, is that I'm squeezing the whole computational game and turning it into one game. Take a Boolean formula, convert it into or compile it into a circuit with the following property that I care about. And that's going to be the essence of computation. Everything is reduced to that. We don't need to do anything beyond that as far as computation, as we will see.
There's a question in the chat also from Ryan Williams. So if I only have to approximate all probabilities up to say, point minus 0.01% as error, as the Bayesian network app seems to do, are these problems still so hard complexity-wise? Probably not.
Okay.
Is it more like ZPP to the NP?
I'm not going to get into that, frankly. Everything I'm going to be talking about here is exact, but maybe towards the end of the discussion, I'll tell you about some weakening of these properties that I'm going to be talking about that could be the basis of approximations. But everything I'm going to be talking about today will be exact.
Okay, good, thanks.
All right, so the basis of these tractable circuits is negation normal form circuits. So what are these? You have 3 types of gates: ands, ors, and negations, inverters, with a condition. Inverters can only appear next to inputs. So you have inputs or inverted inputs and then layers of ands and ors. Now, if the inverters appear within the circuit, you can always convert it to a negation normal form of circuits while doubling the circuit size, at most doubling the circuit size. But everything we're going to be looking at will be NNF circuits, layers, input or negated inputs, and then layers of ands and ors. And now what we're going to be doing is, in the next part of the talk, we're going to walk through a set of properties. So NNF circuits are not interesting. You can do anything with them. They're not tractable. But as we start adding properties, we're going to start getting more and more tractability, and circuits get bigger. For each of the property, I'm going to mention it in 2 ways. Pictorially, which is a very quick way of doing it, and then I'll try to see what happens algebraically under it, because you'll see that each one of these properties correspond to a certain type of Boolean function decomposition. So let's start with the first one. The simplest property is decomposability. And this property is simple. It's a property that every AND gate has to satisfy. If you look at an AND gate and you look at the subcircuits feeding into it, I want these subcircuits not to overlap in terms of variables. So if you look at the subcircuits LK, the circuit PA, the variables do not overlap. Now, this looks like a tree. It's not actually a tree, it's a circuit, because you can see the variable P appear here and appear there, but we're laying out this way for visual clarity. That's decomposability. It's very simple. AND gates, the subcircuits feeding into them shouldn't share variables. And now SAT is linear time on this guy, okay? And you got yourself NP by this simple property. The circuits that result from this property are called DNNF circuits, all right? And if you look what's happening algebraically, here's what's going on. I'm basically telling you, I want you to decompose a function like this one this way. Now, we know that if you have a function that is the disjunction of a number of subfunctions, we know that this is SAT if and only if one of these is SAT. But something else is going on. Each one of these subfunctions is decomposed this way. So not only is this SAT when the first, the second, or third, either of them is SAT, now I can decompose the SAT on this guy into 2 separate SAT problems on this and that, because these guys do not share variables. So because of this decomposition that's induced by DNNF circuits, now you can say SAT F if and only if da da da, right? And similarly, you can take these SAT tests and decompose them, and that's what you can get this in linear time. All right, very simple. First property. Let's look at the second property that gets us to the next class. Together with the property called smoothness. I'm going to mention smoothness next. Smoothness is a convenience property. It's not computationally important, but determinism. Determinism is a property on OR gates. And basically, it says that however input you apply to the circuit, no OR gate will have more than one high input. So high here is red, low is blue. I set all variables to high. You can look at this OR gate, exactly one high input, too low. This guy has too low, that's fine. You can never have more than one high input for any OR gate. If you take this as alpha, beta, gamma, it's saying that they're mutually exclusive. That's basically what determinism is. The decomposability is a structural property. This is more of a logical property. If you have decomposability and determinism together, you can do match sat, chop sat, weighted model counting in polynomial time. If you have smoothness, you can do it in linear time. I'll show you what smoothness is next. And let's take a look at why can I, so now I can count. Now I can count the models satisfying assignment of a circuit in linear time. So, and I'll show you this in just a second how you can do this. But let's take a look at what's going on here. So this is the decomposition we've seen earlier. I want to count the models of this. I cannot add up the models of F1, F2, F3, but determinism ensures that they are mutually exclusive. So I can add the count of this, the count of this, the count of that to get this. And together with decomposability to count the models of this guy, I can just count the models of that guy and multiply by the models of this. So now I have a decomposition, and now you can see why you can do this in linear time. Almost. This equation is not technically correct for a subtlety that I'm going to show you, almost correct. You need something called smoothness, which is a property that says disjuncts must mention the same variables. What does that mean? Because that ensures that we're counting over the correct number of variables. So let's look at this F, which is A or B, right? And I'm writing, this is not deterministic. These are not mutually exclusive. But let me rewrite it like this: A or not A and B. Now it's deterministic. So in principle, I can count this and count that and add them up. Not exactly yet. Here's a third version of this, where I just here, instead of A, I say A and B or not B. This is true. So I really didn't do anything. But now it's smooth because here's a disjunct and here's a disjunct. This mentions AB, this mentions AB. Similarly for that. So what's the significance of this? Now, all of these three are the same. But if you decompose the first one by saying sat on this guy is sat, sharp sat on this, sharp sat on that, you get the wrong answer, because you're going to get a count of 1 here. And what I want to get a count of 2 because I'm counting over the variables A, B. So if you have smoothness, that works. Basically, smoothness makes sure that every variable that you're counting over appears in the formula. Okay, I just want to mention it because it's a property. It can be enforced in quadratic time. There was recent work in a couple of years ago where people like theory folks started and AI folks found some more efficient ways of doing smoothness. But anyways, okay, let's take a look at how this works in practice. Here's a circuit, decomposable deterministic, and I want to count its models. And it ends up being very simple. And what I'm going to show you now is representative of many of the algorithms on tractable circuit. They correspond to simple forward passes of the circuit. So to count the models of this, you simply assign zeros or ones to the inputs. Pretty much in this case, every literal positive or negative will get the value 1. And you just propagate, multiplying at AND gates and adding up at OR gates. So that's at 9. So there's 16 possible circuit inputs, and this is telling you 9 of them satisfy the formula. And all you have to do is this just forward pass on the circuit. So as I said, most of these algorithms, we say polynomial, but actually almost all of them are linear forward pass algorithms. And you can do a lot more sophisticated things now, even with these two properties. You can do marginal counts. I don't want to just know how many satisfying assignment I have. I want to know how many of them sets A to true and K to false. Now I have a lot more queries to answer based on this circuit, not just one query. In principle, I have an exponential number of queries now I can answer. And similarly, you just have to zero out some of the inputs. And again, you add, multiply. And this is telling you out of the 9 satisfying inputs to the circuit, 2 of them have A true and K false. Now, this ends up being important to compute marginal probabilities with model count. All right, so let's look what's going on. If you have a box, that can take a Boolean formula and compile it into a circuit that's decomposable and deterministic, just two properties, you unlock the PP and you can do now weighted model counting. So now you can actually solve probabilistic reasoning on probabilistic graphical models, pending the reduction that I'm going to be showing you later. Now, you can see what's going on here. I'm using a Boolean circuit to do an arithmetic computation. So really, here's what's really happening. So you can think of having synthesized an arithmetic circuit. And this story was told a couple of decades ago. There is a lot that can be said on these resulting arithmetic circuits. And one of them is not only they can be used to do marginal counts, you can actually differentiate these and compute partial derivatives with respect to the inputs, and that ends up being meaningful. They give you even more probabilistic quantities. We're going to get back to this, but I just want you to now, in your head, to see how this story of Boolean circuits is synthesizing a story about arithmetic circuits and tractable arithmetic circuits we're going to come back to later. Let's go to two more properties, which will give us more circuit types and allow it to hit even higher complexity classes, NP to the PP and PP to the PP. What these two properties that we're going to talk about next, and they're pretty important, at least practically, they've had a lot of impact. One of them strengthens decomposability into something called structured decomposability. And the other one strengthens determinism, and each leads to new circuit types. Structured decomposability says, okay, I want decomposability to be a little bit more principled. I'm going to give you something called a V-tree. What is a V-tree? A V-tree is simply a binary tree, the leaves of which are your variables. And you can use any V-tree. I don't care. Okay? This is one of them. And what I want is for every AND gate, I'm going to now assume that every AND gate also has only two inputs. And when you look at the variables, an AND gate, it should map to one of these V-tree nodes, in the sense that if you look at those variables, they're in the one of the subtrees, and the other variables are on the other subtree. Okay, so you look at all of these AND gates, they conform to that V-tree node. They're doing their decomposition in a systematic manner following that V-tree. You look here, those also conform to the V-tree. They map to one particular V-tree node, and they decompose their inputs according to that. You add structured decomposability, you can do more, and you also get one more exponential separation. So by the way, going from decomposability to determinism, there is an exponential separation. This gives you exponential separation. But if you look at algebraically of what's going on here, really what this is telling you, I want you to decompose your function or Boolean function or Boolean expression recursively as follows. I pick a split of the variables, xy, of your Boolean function, and then I want you to write it like this. As a bunch of g components or x components, y component, You can always write a Boolean function this way for any x and y. But then you need to know how to split the variables. The V-tree tells you how to do that. So what's happening here, when I give you a V-tree, I'm saying, okay, when you start, pick your x variables so that they're in the left subtree of the roots, and the y variables in the right child of the roots. And now you can do this and repeat. So if you now want to decompose these y components, now you go and basically use V-tree node number 2, and this is your x and y. So basically the V-tree gives you a recipe for how to decompose your Boolean function. And just to give you an example of what can be done now once you have structured decomposability, you can now multiply or conjoin circuits in polytime. You couldn't do this based on DNNFs. If I give you two DNNF circuits and I say conjoin them, while guaranteeing that the result is a DNNF circuit, we cannot do this in polytime under complexity assumptions. If you have structured decomposability, you can do this in quadratic time, actually. And with additional properties, we're going to see that we can unlock more complexity classes. If you want to visualize this differently, here's decomposability versus structured decomposability. In both cases, G and H's do not share variables, but here they're actually doing the split of the variables in a systematic fashion. Okay, one more property, and we try to wrap up this part here. So what we'll do next is strengthen determinism, right? And just like we strengthen decomposability. And we're going to do it by adding one more property on XY decomposition. This is a type of decomposition that I called XY partition as opposed to decomposition Y, because it is an XY decomposition with one more property, which end up actually having all kind of implications. So again, you give me the Boolean function, and we pick up how to split its variables into an X and Y, and we write it like this. Now I'm going to distinguish between the G and H. I'm going to call these G's primes and these guys subs. Why? Because now I'm going to require that the primes are mutually exclusive and exhaustive. So if you pick up any of these two primes, they conflict and they're exhaustive. So they form a partition. Now, why does that end up being significant? Well, if your subs are distinct, if the subs are distinct, you do not have two H's that are the same, then we call this a compressed XY partition, and that happens to be unique. So once you decide how to split the variable of your function into X and Y, there is only one way to write one of these expressions that is compressed, which basically means that this would lead now to canonical circuits. And again, we have and canonical once you fix your V3, because look what happens. You give me V3, and then I want to decompose this function into this. The first node tells me how to split X and Y. There is only a unique XY partition that's compressed. So I got this guy, and there is no choice on how to do this. And now I'm going to take this guy and decompose it further. And now I know how to split the variables. So now that you know how to split the variables, there's only a unique compressed XY partition. So now I'm going to get actually a canonical decomposition. Now, once you have this property, the circuits that you get, I call these sentential decision diagrams or SDD circuits. And you'll see why this name is pretty interesting. But this circuit is actually an SDD. It does satisfy the partition determinism property. And if you think about it, it's actually made up of fragments that look like this, right? Where I have a function and it's being decomposed as we've seen. Now, the G1, G2, G3 are a partition. What does that mean here? That means regardless of what circuit input you apply, precisely one of the G's will be high and the other two will be low. In this case, this is the high and the other are too low under this particular input, which means that this fragment is, in this case, just passing the value of this guy. So you can think of this fragment as making a decision. It's a decision node saying, should I pass H1 or H2 or H3? And the guy that gets passed is the one that has a corresponding high prime. All right, so that's why it's called decision diagrams. Now, why is it called sentential decision diagram? Because the decision that's being made here is made based on testing the value of an arbitrary sentence, G1, G2, or G3, in contrast to binary decision diagrams, which, as we'll see next on the next slide, is a special case of this, where the decisions are being made on a variable instead of an arbitrary sentence. So these are sentential decision diagrams. Now, it turns out, if you have an SDD that is based on an appropriate V3, I'll tell you what that in just a little bit, then these circuits can do match-match-sat in linear time. So what does that mean is, if let's say you're and their functional version, if you're interested in doing SDP, remember the SDP query on Bayesian networks, which is what is the probability that my decision will stick if I were to observe these variables? If you take your Bayesian network, write out the Boolean formula, as I'm going to show you later, and compile it into an SDD circuit with an appropriate V3, then now you can do that query in linear time on the SDD circuit. Okay, pretty remarkable. Now, I skipped how you do the eMatch-SAT class. That requires another circuit type that I'm skipping, but it's called certain type of decision DNNFs. We can cover that much in this talk, but I'll give you a pointer later where you can track all of the details down. But let me just say something about OBDDs, because it's important. OBDDs, as we know, very important. Some people would tell you they're perhaps the most studied tractable representation of Boolean functions. What do they have to do with this? Well, they're just a special case of what I just showed you on the previous slide, if you adjust for notation. So if you take a decision node like this in an OBDD, we know OBDDs, they're decision graphs, right? The things are 0, 1. If you give me a variable instantiation, you start at the top and you follow the edges, high, low, high, high, and then you get the value of the Boolean function. But they're actually just circuits. If you take a node like this, and you can think of it as just a circuit fragment, that's what's going on, a multiplexer. Depending on X being true or false, I'm choosing to pass this or that. That's actually the XY decomposition we looked at, except in this case, the primes are just either a variable or its negation. In our case, XY decompositions were more general. The primes were arbitrary sentences. Now we're restricting them to. So in fact, here's two interesting observations. If you use a right linear V3, or what's known as a right linear V3, in which the right child of every internal node, the left child, is a single variable, you are forced to always use XY decompositions in which the X is just a single variable. And that actually ends up generating SDDs that are OBDDs. So the notion of partition determinism that I talked about subsumes Shannon's expansion, which underlies OBDDs. Again, here in Shannon expansion, I am doing exactly what I talked about, but I'm splitting one variable and everything else. Here, I'm allowing to split the variables into any two sets without a restriction on the counts of the two sets. And it turns out that branching on sentences as opposed to individual variables leads to exponential separation. So SDDs are exponentially more succinct. You will have Boolean functions that will blow up for OBDDs, but will not blow up for SDDs. And that's basically what's going on. Now, just a word on this notion of what V3 should you use. Now, if you remember, in the problems for NP to the PP and PP to the PP, we had to split the variables into X and Y. And to solve these problems using SDDs, you have to pick a V3 that is arranged in a certain way for these X and Y. Let me show it to you pictorially. Okay, you don't have to read this, but you need to have a node on the rightmost path where everything outside that is X and the rest is Y. So you cannot use just any V3. You need a V3 that has a particular structure, and that basically allows you to do these problems. We call these constrained SDDs. We call the V3s constrained V3s. Okay, we're almost done with this part. Let me just say a couple of general remarks before we finish this component. So as I said, I just exposed you to part of what happens under the area of knowledge compilation. This notion of studying these three dimensions of properties, computational power, succinctness, is under what's known as the knowledge compilation map, which was the title of this paper that basically started this methodology for doing things this way. There was a workshop, 5-day workshop dedicated just to the subject in France about 2 years ago. There is a tutorial there that these slides are actually, this slide is from it, that shows you an example of containment. So as I add properties, I start going down. You can see OBDDs has the strongest type of properties compared to anything else that we've talked about today. They give you the most computational power, but they're also the least succinct. You can see some of what we know about succinctness. This means exponential separation. Decomposability, you add determinism, you get exponential separation. I gave a tutorial last summer at the POTS conference, theory conference, and there was a paper attached to it, an extensive survey, which I'll just give you a pointer next. You can find there a lot of pointers to knowledge compilers, model counters, this is actually the paper. It's called 3 Modern Roles for Logic in AI. It has broader scope than I'm talking about today, but you'll find it online, and you can use it to chase a lot of the references on things. Before I end the segment, let me just also mention that even though these developments have been mostly within AI, there's been a lot of interactions with other areas as well. Just a couple of knowledge compilation meets. Knowledge compilation meets, it's basically Tractable Circuits meets as well. Now, because I do have a segment towards the very end about knowledge compilers. I don't know how much time we'll have when we get there. So let me just have one slide here before, so in case we don't manage to cover that. you can ask yourself, okay, so everything now is boiling down to this notion of taking a Boolean formula and compiling it into a circuit of an appropriate type. How do I do that? There's two classes of knowledge compilers, bottom-up and top-down. The bottom-up may be more familiar. Well, actually, they're both familiar to people, I guess, in the following sense. So bottom-up is how OBDDs traditionally have been compiled. If you're familiar with something like CUD, the main tool for OBDDs, it's based on bottom-up compilation, which is simply you compile every ingredient of a Boolean formula and you just combine. So if you want to compile alpha and beta, you compile alpha, you compile beta, and then you conjoin the two guys, two OBDDs. The reason you can do this is OBDDs have what's called an apply operation, which is an operation that can combine any two OBDDs using a Boolean operator in quadratic time. You can do the same thing for SDDs. SDDs also have polynomial time apply operation, and therefore you can actually build them that way. Both of these methods rely, so they'll tell you, wait, it's so straightforward. You just take a Boolean formula and start apply. Nah. Both of these are canonical. In this case, if you fix the variable order, you have a unique OBDD. In this case, if you fix the V3, you have a unique SDD. So it all boils down to finding the right OBDD or right V3, and that's where all of the work happens. Now, top-down compilers, which is the one I will talk about if I had a chance, work completely differently. They are based on search algorithms like you use for SAT or sharp SAT, except that they keep a trace behind them. So you can take a search algorithm like DPLL or exhaustive DPLL and keep a trace, very simple notion of keep trace. If we get to that part, at least I'll have to tell you what a trace is. And then you'll see that the trace is a circuit. So by running these algorithms and keeping trace, they spit out circuit compilations. And the interesting story is there are variants of these exhaustive DPLL algorithm. Each one of them leaves a trace in a different tractable circuit class. And there are implications for this compilation method, because if I can establish the trace of an exhaustive search algorithm, exhaustive DPL search algorithm, I can tell you a lot about its complexity because of what I know about tractable circuits, their succinctness, and what can you do once you have these tractable circuits. Okay, so I'll leave it at that. And just a couple of words. The space complexity of these guys end up being way better than that. These guys can work on any Boolean form. These guys typically require CNFs because they're based on these search algorithms that typically require CNFs. So there is trade-offs between these guys. Okay. What I'd like to do next is...
There was a quiz. I missed a question, actually. I see now. Sorry about this. So the question about SDDs and OBDDs. Are SDDs more powerful than OBDDs if you're also allowed to use additional variables?
If you are allowed to use additional variables, I can't recall immediately result, but I can suspect once you add additional variables, you can do all kinds of things, typically. I can't recall immediately now a construction.
And there's an added comment in the chat that the STD is the same as an orthonormal expansion, page 48 in Boolean reasoning by Frank Brown. Karam Sakala. I was just reading it out for the record. Anyway, but yeah, usually I guess like once you have these extra variables or extension variables, then all bets are off, no?
Yes, I mean, you know, additional variables is a very powerful thing. So I can't recall something immediate on that. By the way, there is an SDD package, which is open source, available from my group. It's in C. You can find it online. It's called the SDD package. Just type SDD package UCLA. You can find that. So, okay. So any other questions, Jacob, or should we move on?
Can I just follow up on my comment? I think what you're doing, Adnan, is just having that V3 determine the orthonormal expansion. So the SDD, you get a different SDD if you have a different V3, correct?
The SDD is determined by the V3.
Yes. So I'm just pointing out that this is the, you know, it's the orthonormal expansion has been known for a while as an extension or a generalization of Shannon-Boole expansion, where you have an orthonormal basis to decompose. But I think what you're bringing here is the V3 that actually gives you a particular SDD, correct?
Right. In fact, the whole game of compilation is finding the right V3. And if you look at the SDD package, it's all about dynamically searching for V3s in a similar fashion that you find.
Right.
Now, but since turns out the question is from Karim, I think, remember, Karim, we had this discussion a while back in one of the lobbies, and it turns out that it's not exactly what you're saying, but I'll follow up with you on this.
Okay.
Offline.
All right.
All right. Very good.
Adnan,
Yes.
Quick question. Could you remind us again what a V3 is?
What a V3? V3 is simply a binary tree. That's it. Where the leaves are tagged with your variables. So take your variables and arrange them in a tree structure, binary tree structure. That's it. All right, full binary tree. So here's a V3. And as I said, a special type of V3s is the right linear one. Now, the one that is shown here. That's a V3 as well. But if you look at this V3, it's like a total variable ordering in a sense. And that's why when you use V3s that are right linear and construct an SDD, you actually get an OBDD. Why? Because look what this guy's telling you. That tells you if you want to decompose your function, start at the root. Split your variables into A and then B, C, D. If you apply the XY decomposition with that split, that ends up being the Shannon expansion. So this forces you to always decompose your function using Boole's or Shannon's expansion, right? And then you always get, so you get OBDs as a special case of SDDs because they correspond to a particular type of V3s. But I showed you V3s that are not right linear before.
So V3s give you a variable order that you can use to construct your BDD.
If they're right linear, but if they are not right linear, they give you a recipe for continuously splitting your variables. Remember, this is what we're doing. We're taking a Boolean function, and if you split its variables into X and Y, then you can do this. What the V3 is telling you is how to split your variables of a Boolean functions into two sets at every step of the decomposition. Okay. They're not a variable order. They're a more general notion of a variable order. Yeah. There are a dissection scheme.
But one of the use cases could be that they can give you a variable order as well.
Exactly. If they're right linear. If they have a certain structure, they end up giving you a variable order.
So another question I had was here you're, if I understand correctly, going from CNFs to circuits or circuits to circuits, right? That's what you mean by knowledge compilation.
No, we're typically going from Boolean expressions to circuits, typically from CNF to circuits. That's what we're typically doing.
Yeah. And I wonder if a lot of this, how one could use this to inform pre-processing, in-processing, and encoding in the context of SAT solving. A lot of this could be useful if you were to go from, say, CNF to CNF, for example. Is that?
That is not the scope here, because this is where we get into the business of knowledge compilation. The idea here of knowledge compilation is when I'm going from something to something, the new guy I'm going to has to be tractable in some sense.
Right.
So CNF to CNF is not of interest to this area because the output, or what we call the target, there's the source and the target. The target is not tractable. So for knowledge compilation to kick in, you need the target to be tractable in a sense. Right. And it's the other way around. You can use preprocessors for SAT to help with knowledge compilation. And actually people have done that. So, okay. Very good, guys. Let me tell you the core reduction. This is interesting. This is
so just a question of order. At some point, halfway through, we should be getting a small break. I think usually, so I don't know if now or slightly later is a good time. I'm just.
Let's do this reduction because it's brief, and then take our break. Okay.
Fantastic.
Does that work, Jacob? Okay.
That works.
It would be a good transition. Okay. Core reduction, folks. Remember this picture. And the idea is you can take these, models and write a Boolean formula, and then Then you like, wait a minute, how does that happen? Numeric Boolean. Well, you get to see now how this works. I'll show you the core reduction that from 2 decades ago that I proposed. It was the basis of at least another half a dozen reductions over the following decade, and it's pretty simple. if you have a Bayesian network like this, 3 variables A, B, C, you have what we call these parameters, these probabilities. And for a root node, it's just distribution. For a node like this, you have a conditional distribution on B for every state of A. So these are 2 distributions, actually, 4 parameters, but 2 distributions, 1 distribution and another distribution. Similarly here, we call these parameters. These are the real numbers. Now, if you look at what is the distribution that's synthesized with the Bayesian network, it looks like this. I'm not going to tell you why, but I just want you to see how systematic it is. So these are all of the variable instantiations. And what you're doing here is for the probability is simply for every variable, you go and pick up one of the parameters, one from here, one from here, one from there, and you multiply them. And which one you pick is the obvious thing. You pick the ones that are compatible with that variable instantiation. That's pretty much it. So you can see here, every probability of a row is the multiplication of 3 numbers because I had 3 variables. If you had 10 variables, you end up having multiplying 10 guys. The reduction is based on a very simple concept. For each one of these real valued variables, I'm going to introduce a Boolean variable. All right. So this has 10 parameters. I'm going to add 10 Boolean variables in addition to the variables of the Bayesian network. And you write out Boolean expressions that look like this. I have to apologize. These, instead of being A given B, should be B given A, C given A. But look what happened here. The A's and B's are from your Bayesian network. And then these are the new guys that I introduced. I introduced one of these for every one of those. And intuitively, what this means is that parameter is present. Because if you look at this row, out of the 10, 3 are present and 7 are missing. And that's what this guy's trying to capture. Now, by construction, and this yellow Boolean formula can be written out in linear time. You can see it's pretty simple. If this is true and this is true, if and only if that parameter is present. False and false if and only if that parameter is present, and so on. By construction, the number of satisfying assignment for this guy is precisely the number of rows here. So this guy has exactly 8 models. And by the way, we're reducing this to weighted model counting. So the weights are all literals for these variables are 1. The only literals that get a real value is these guys. They pick up their corresponding number. And what happens, if you look at any model of this Boolean formula, it's going to look like this. There is a portion which corresponds to these variables. In this case, this is essentially true, false. That's, I think, true, false, second row. And a bunch of these positive guys and negative guys. And by construction, the positive guys here will be precisely corresponding to these parameters. So given this mapping of weights, the weight of this model will be exactly the probability that you care about. And then you basically can use this to do weighted model counting. Pretty simple. All right. Now, this is the vanilla flavored reduction. This is the first reduction that took probabilistic reasoning and wrote it as a weighted model counting problem. It's the one that used for the other kind of problems. And let me just say one word before we take the break. This reduction that I just showed you is only specific to the topology of the Bayesian network. The more fancier ones can do more things by utilizing the values of these thetas. In particular, if thetas are 0s or 1s, you can do better. If some thetas are equal, which correspond to something known as context-specific independence in Bayesian networks, then you can even write more refined reductions, and you can basically compile them better and so on. So this is basically, there's actually a good survey from, now it's 10 years on this, a whole slew of reductions based on this idea that I just told you. This is kind of now the standard reference for this use of weighted model counting to do probabilistic reasoning. Later, I'm going to give you a link or show you. I taught a course on this subject. There's 35 hours about what I'm talking about today. And 2 of the lectures are about reductions, 2 hours on what I just did now in a few minutes. This course is online now. So this is the time for a break, Jacob. So I don't know how long you want to take a break.
Fantastic. Yeah, what do we say? Let's 10 minutes?
10 minutes sounds great.
So then reconvening at something like 44 minutes past the hour in whatever time zone you're in.
Sounds good.
Right. Fantastic. Thank you so much.
All right. Umid, can you still hear me? Is audio back? Can someone confirm audio?
Yeah. Yes, we hear you well.
Very good, thank you. So we'll start in a minute, Jacob, right?
Yes. There was a comment meanwhile in just regarding this representation. So Paul Beam was commenting that for extra variables with OBDDs, they would not help at all. The minimal form is canonical for a given variable order, and the extra variables would just get minimized away and be skipped. And the same would be true for any representation that simplifies under restrictions.
Very good.
And then there's a comment from Karam that the SDD is simply an orthonormal expansion, does not diminish its utility since there can be many orthonormal bases, the G functions. The question is how to get a compact expansion, which I assume the V tree is used for. Is it possible to find a minimal expansion?
Question. By the way, since we're here and this was mentioned, the V3s, we're not going to talk about this today, the bottom-up compilation, but there should be a lecture on this in my class that I'll point you to. If you look at OBDDs, people have spent significant efforts to try to search for variable orders. In fact, if you look at a package like CUD, you'll find that the majority of it is these heuristics and the zillion ways in which you can actually heuristically try to find variable orders. In the SDD package, which I spend a lot of time actually developing, I try to give primitives for people so that they can explore search algorithms very easily. So you'll find very high-level primitives that will take a V3 and say, rotate a node left, rotate it right, swap its children, and then all of the low-level engineering that has to take place as far as adjusting the SDD to conform to the new V3, that happens on your behalf. So it is set in a way where people can explore new heuristics and algorithms for V3 search very easily. And I do hope some people will, or some of their students will try to do some of that. I think we need a little bit more heuristics for V3 search. Because as you know, just like OBDDs, the difference between a good V3 and a bad V3 could be exponential as far as the SDD side. So check out the SDD package, which has both a user manual and quick start menu. So shall we start, Jacob?
Yes, please go ahead.
Okay. Very good. Okay, so with the segment, we'll talk about tractable arithmetic circuits. And this is actually an interesting story because, as I said, there are two tales. There is the original tale, which I alluded to, where tractable arithmetic circuits is a side effect of tractable Boolean circuits in the sense that I'm looking at something like a Bayesian network, and then I reduce it to a weighted Boolean formula. I compile it to a tractable Boolean circuit of appropriate type. And the kind of operations that I'm doing on this Boolean circuit effectively induce an arithmetic circuit. So that was the original story from about 2 decades. But what we're going to do now is something a little bit different. And why is that? I'll tell you why. We're going to cut out the middleman, in a sense, and simply talk about the relationship between a Bayesian network and an arithmetic circuit. And try to tell a story that is more streamlined. Why? Because what happened is these circuits, while they were originally introduced as a computational device, the machine learning community picked on them and start to do other things, which is they start to learn them from data. They start to handcraft them. So there is no longer a reference distribution. And that can lead to issues when you lose reference of the basically reference distribution. And there were issues which demanded a new look at all of this. And I'll give you, it's a pretty short story. But not only are we going to tell this story with going between Bayesian networks and arithmetic circuits, we're going to tell it even more abstractly. I'm going to show you the notion of a factor, which you're familiar with. The notion of a factor comes from probabilistic reasoning. And we're going to talk about the relationship between an arithmetic circuit and a factor. And we're going to give you the gist of the story. The upshot of this story is, beyond giving you a more direct semantics for what's going on, is that in the space of these developments, the last about 10 years ago, there was a major development, which at least, got me wondering about things, and we're going to find the solution to that. So what is a factor? A factor is simply a table over some variables and a number attached to each row in that table. So it's a mapping from variable instantiations to numbers. And the idea is this could be coming from a Bayesian network. So a Bayesian network specifies one of these, and these are always exponentially sized, right? They are the ones also induced by weighted model counting, but we don't care where this factor came from. What I care is I have a factor and I'm going to define two computations with respect to it. So the MPE computation, which is find me the maximum row that satisfies some event. So you tell me B is false, and you tell me find me the row that is compatible with B is false and has the highest value. That subsumes SAT, right? Because in SAT, these would be 0, 1, and you're trying to find a guy. Okay. Now, the marginal probability is I want you to sum the weights of all of these rows that satisfy some condition B equals false. And you can see this subsume these guys. Now, again, why is this important? Because I'm going to now talk about only the relationship between an arithmetic circuit and one of these tables. Now, this table, as I said, is usually represented implicitly by a Bayesian network, which is not exponential in the number of variables, or a weighted model counting problem that is not exponential in the number of variables. Now, the question that we're going to be asking is, when does an arithmetic circuit compute these quantities correctly in linear time? And what we're going to find out ourselves doing is defining only two fundamental notions and asking three fundamental questions that we'll see next. Listen, and there's an interesting complexity puzzle there that's going to come up. So what is the first notion? The first notion is the notion of NAC, which we're going to define it now simply as a computation graph that has multipliers and adders and constants and these indicator variables. What are the indicator variables? For every variable and value of it, you have one of these indicators. So in this case, I have two Boolean variables, A and B. There is an indicator for A false, indicator for A true, indicator. Okay, that's it. We're not going to assume anything, except that once you give me your discrete variables, that defines the indicators. That's one input to the circuit. And then I have constants and then multipliers and adders. No other assumption. And I just need one more notion, which is how do you evaluate a circuit under some variable setting? So if you give me A is true, B false, or another setting where A is true, but you're silent on B, how do you evaluate that? It's very simple. We replace the indicators by 0, 1 and evaluate in the usual way. So in this case, if an indicator subscript is compatible with the input, it gets a 1, otherwise a 0. So here I have A true, 1, 0, right? In this case, I'm silent on B, so both indicators for B gets the value 1. That's it. That's all I need. Now, here's the thing. The thing is, if I give you one of these circuits and I tell you what factor does it represent, or what factor is it trying to do computations on, you have to settle this question. Without settling this question, there is no meaning for making claim about correctness. And this is one of the issues that was missing from the machine learning literature treatment or follow up on what I did earlier. So we're gonna, once you define that, once you define what is it the factor, what is the reference factor, then you can start asking the second two questions and say, does the AC compute the marginals correctly? Does the AC compute MPE correctly? Now, how do you find out what is the factor that is represented or the reference factor? It's very simple. We evaluate the circuit under full variable instantiations. So this is a circuit that is concerned with two variables A and B, and I want to know what is the factor that this guy is claiming to do efficient computations on. Very simple. We go ahead and say, let's set the values of A and B to these values and evaluate the circuit. We know how to do that, how to set the indicators when A is true and B is true. And we do that, we get 3, okay? We do it for A true, B false, we get 4. Okay, now this is my starting point. Now I said, okay, you're trying to make claims on the circuit. I know now what factor we're talking about. Tell me, what are you claiming? Okay, this, what I just told you, the obvious was missing. And people had issues where say, oh, this circuit does not compute this. I modify it and now it can compute this efficiently. In the process of doing this, they changed the underlying factor. So you were having a hard time doing a computation. Now it's easy, but on a different problem. All right, because this was missing, this concept. Now, here's the first observation. If the only goal is to get a circuit to compute a factor in the sense that I just told you, that's not interesting, and that's easy. Actually, if you give me a Bayesian network, I can always, in linear time, construct a circuit that computes the distribution of the Bayesian network in the sense that I've mentioned. The interesting thing is when we want to compute marginals. What does it mean to compute marginal? I want the circuit to compute the right quantity when I give it a partial variable instantiation. So in this case, if I only tell you A is true, I don't tell you anything about B, will this do the right thing? Now, what is the right thing? We know because we have the factor. If you tell me A is true, the value that I should be getting is 7 because there is 2 rows that are compatible with A is true, and I want the circuit to be able to add them. Will it do it? Okay, well, let's see. If you do this here, it doesn't. You get an 8. So this circuit does not compute marginals for this particular factor. Now, let me show you another circuit, this circuit. This circuit has the same reference factor, right? We can check it. Try. At A true, B true, it will get 3. At A true, B false, will get 4. It's okay. Now, this one, however, does compute marginals correctly. So if you go and evaluate it at only A, you'll get a 7. If you evaluate it at B false, you'll get a 16. If you evaluate it at truth, so you wanted to add all rows, it will do the right thing. What happened? 2 circuits, both have the same reference distribution. One can compute marginals, the other does not. What happened here? Okay, let me show you another query. The other query is MPE. MPE is, remember, I want to find the row with the highest value that's compatible with the particular evidence. In this paper, we showed that for a circuit that with the right properties, we're going to get to this. If you turn the adders into maximizers and evaluate the circuit at a particular input, then the number you're going to get happens to be the probability or the value attached with the highest value. So, and this result said even more, said you can go back to the circuit and find a subcircuit. You start at the top and you follow the children that has the highest value of a max node. And for a multiplication node, you follow all of the children, you get a subcircuit. And that circuit identifies also the identity of the row and the value. So let's take a look. This circuit computes this factor, but when you move the adders to multipliers, it doesn't do the right thing for the MPE. So what's going on here? Okay, here's what happens. What happens is, if you give me an AC that computes a factor in the sense that we mentioned, whether it actually computes MPE and whether it computes marginals depends on what properties it has. And guess what these properties are? Decomposability, determinism, and smoothness. You can define these on arithmetic circuits, just like you did on Boolean circuits. Decomposability and smoothness are simply structural properties, so there is no difference. Determinism, just instead of saying at most one true instead of this, you can say at most one non-zero other. Okay. Now, there's 2 sets of results, the salient results in this area. The one, and the next slide that I'm going to show you, both results did not appear in the form I'm going to show you next. But that's the gist of what's going on. And let me just say, when the machine learning folks picked on this, they renamed determinism into selectivity and smoothness into completeness. All right. Now, the first set of results is that if the AC is decomposable, smooth, and deterministic, then it will compute marginals and MPE correctly. Okay. Now, the surprising result came in 2011. I'll give you the specific citations for these papers in just a second. it turns out that if the circuit is only decomposable and smooth, it will also compute marginals. Believe it or not, you don't need the determinism. Now, this is now a puzzle, because marginals is like counting. And this is kind of suggesting that I can count without determinism, which is weird. But we're going to resolve this puzzle in just a second. But the original claim, these circuits that were both decomposable and smooth were called SPNs. And the original claim that SPNs not only computed marginals correctly, they also computed MP correctly, and that turned out to be wrong. No, you can't. If you only have determinism, decomposability, and smoothness, an AC will compute marginals correctly, but it will not compute MP correctly. Now, later, when people found out the mistake, they corrected it by saying, let's add again determinism, which they renamed selectivity, and then they talked about selective SPNs, and they said those compute both marginals and MPE, except that SPNs are exactly decomposable deterministic smooth ACs, and we knew this result from before. Now, here's the interesting thing. The interesting thing is this fact that I can drop determinism and I can still compute margins. And I'm going to say two things about it. One of them is that adds to the intrigue, that there is an exponential separation. So there is a class of factors that you can represent them by poly-sized decomposable and smooth ACs. So you can find SPNs for these factors that are polynomially sized. But if you insist on determinism, they'll blow up. So there is an exponential separation, which is like, wow, I can still compute marginals using a circuit type without determinism, and that could be exponentially smaller. But here's the big catch. And this account that I'm just giving you now is recent compared to the history of this area, which is just from a few years ago. Here's the catch. The catch is the following. And this is important. This is for me was the biggest puzzle from a complexity point of view. Look at a factor. A factor is, the numbers in that factor are specified by these literal weights, which is the product of literal weights. I get this. Now, if you tell me I want an AC for this factor that is decomposable, deterministic, and smooth, I can always find one where the constants of that AC can be restricted to these literal weights. And in fact, I showed you even a reduction for that. So the question is just about enforcing decomposability, determinism, and smoothness. I don't have to worry about weights. I know which weights to use. That no longer holds if you drop determinism. If you tell me I want a circuit that computes a factor, and it's only decomposable and deterministic, it's only decomposable and smooth, but not deterministic, there is no longer a guarantee that you can find one if you restrict yourself to these constants of the circuit. Another way of stating this, finding an SPN that computes a factor may require you to search for circuit weights. So it's not just a structural property. It's not just trying to impose decomposability and determinism. You have to search for weights. Another way of looking at this, relaxing determinism comes at the expense of having to search for circuit weights. Now, this already preempts the puzzle, which is, can I use this for counting, right? In counting, these are 0 1s, right? And that means you cannot just restrict your circuit to have 0 1s. You can find a decomposable and smooth circuit that computes model counts correctly, but its weights cannot be 0 1. You have to search for those. Now, this is very interesting from a complexity point of view and a computational point of view, resolve the puzzles. From a learning point of view, it's not as much of a big deal because people learn these things. So part of the game is to search for weights, right? So to what extent you will be intrigued by this result or not is to what extent you're interested in these circuits from a computational point of view versus learning them from data. So let me just mention a couple of remarks on these things. This area, there's some confusion about things, and partly because the notion of ACs, SPNs, and recently people start using the term probabilistic circuits. They've been used in two ways. One, in a loose way, to simply mean computation graphs with indicators, constants, multipliers, and adders, and in a more specific way, to refer to arithmetic circuits with particular properties. So the experts, people who work very closely with this, they will take ACs to mean decomposable, deterministic, and smooth, SPN to mean this, selective SPNs is basically just ACs because they have the same properties. Recently, people start using probabilistic circuits as an umbrella term. Interesting, but actually restrictive, because these factors do not have to represent distributions. They're just mappings from instantiations to numbers. So there's really no specific tie to probabilistic reasoning, but that's where most of the applications are. And you can induce more circuit types. We didn't talk about PSDVs. Those are arithmetic circuits that are based on structured decomposability and partition decomposability. So they have stronger properties than these guys. They're just probabilistic SDVs. And if you get into this area, on the machine learning probabilistic reasoning side, you'll see a hodgepodge of things, and it gets complicated by people keeping renaming things. Focus on the properties. Everything that's happening is actually due to underlying properties, and pretty much every property we know of there came from the Boolean side. Let me just give you, I promised some citations, because if you look at the chronology there, the original formal treatment of arithmetic circuits in this context was in this paper. This was the algorithm that introduced the MPE finding the subcircuits and turning adders into maximizers. This is the paper that was the first to say, let's not just use this as a computational device. Let's try to basically kind of use them as a learning device. And this is the paper that actually dropped determinism and introduced the idea of handcrafting ACs. The discussion that I gave you is based on this, which is the most recent. For a theory audience, this would be highly recommended. Extremely formal, tries to really give a treatment of what happened in the literature before then, and tells these stories of the two tales that I mentioned. So let me see how much time I still have. Very good. What I have is two more topics. One is I want to talk a little bit about knowledge compilers and a few words on explainable AI towards the very end. So unless there are questions, I'll just go ahead and talk about this. Probably I have what, I think 25 minutes. Yeah, I'll do maybe 15 on this and 5 on the other.
There are no questions in the chat that I can see. There's been a discussion about this minimization, that it's probably NP hard to minimize. And then the question is whether you can somehow, if you don't need the exact minimization, whether you can do better. But I see no questions.
Very good. Okay. So folks,
go ahead, please.
Thank you. So knowledge compilers, right? I showed this slide before, and again, the idea is either bottom up, top down. I'm going to talk a little bit about this. At least this part here is quite familiar. This quite is similar. Jack was saying there was a discussion on minimization. Check out how SDDs are minimized and how this V3 search happens. It's pretty exciting. But we're going to talk about the top-down notion of compilation because it's interesting from a couple of points of view. So the idea is I'm going to take an exhaustive DPLL algorithm and I'm going to add a trace to it. I'm going to have it keep a trace. And then what we're going to, when we do that, we're going to turn it into a knowledge compiler. And the idea is the trace ends up being the circuit compilation. It's like a rewrite for the input formula. This is not a theoretical exercise. We build the first compilers that way, and then we formalize this notion, and other people, I think the Toronto compiler, D-sharp, was based on taking sharp set and keeping a trace and then turning into a knowledge compiler. So the idea is very simple, pretty powerful though. What does it mean to keep a trace? So if you look at exhaustive DPLL, what's going on here? You have a Boolean formula like this, and then let's say we're doing DPLL, right? So you take X, I'm trying to find a satisfying assignment. X is 0, I get this, X is 0, Y is 0, unset. Then I try Y is 1, then I try Z, So at this point in the search, I found a solution, a satisfying assignment. If you're doing DPLL, you stop, done, I solved the problem. Exhaustive DPLL, I keep going. one of the reasons is I want to count how many satisfying assignments. So you go and you run to exhaustion. So I'm going to try x equals 1. And then when you get y, then you try that, and now I found another solution. Again, if the goal is to find simply a solution, I'm done again, but no, I keep going to exhaustion. So now this is determination 3 after having run DPLL to exhaustion. Now, what is a trace of this process? A trace of this process, if you look what happened here, that termination tree is actually a circuit rewrite of your input. What happened here? You look at a node like this, we've seen this. If you have this X, if false go this way, true go that way, you can think of this as this little circuit fragment that says not X and that, X and that or, right? So by systematically keeping a trace and recording it in this fashion, I got the rewrite. So I compiled the formula. Okay, this is not an interesting compilation because that's a tree. Now, you can do various things, both on the search itself and how you keep a trace, which end up actually giving you different circuit types and different knowledge compilers. So at the simplest is this notion of dealing with redundancy when recording traces. So if you look at this trace, it is quite redundant, right? These portions are the same. So let's try to not do that. And you can do something very simple, which is do not record duplicated nodes. So let's start with terminals. No duplicate SAT nodes, no duplicate unsat nodes. That's easy to implement. But now I have still duplicates of these decision nodes. You know, the OBDD literature tells us how to do this very easily. There's something called unique node table. So when I see something like this, before I create it, I check if I had one like it. And if I did, I just point to it. So I get that. Okay, so now we're keeping a trace of DPLL and with a little bit of care in recording the traces. Well, guess what? This is an OBDD. We just compiled an OBDD. Now, that's not how OBDDs have traditionally been compiled. That's not how CAD does it. OBDDs are done in a bottom-up fashion. And in fact, when this was first introduced, I think it was a while, this led to new complexity guarantees. Using this technique, you were able to give bounds on the time of OBDD construction, not just on its finite size. But you have to realize that what happened here is the reason we got an OBDD is that this was exhaustive DPLL, but we fixed the variable ordering, which is not typically what you do. So when I was going down the search tree, I'm always visiting variables in the same order. If you don't do that, which is the normal with exhaustive DPLL, then you get what's known as basically FBDTs, right? Free binary decision diagrams. So now exhaustive DPLL with keeping a trace in the classical fashion or the vanilla flavored exhaustive DPL will compile FBDTs for you by keeping a thread. Now, you can take this further. So one idea that was introduced later in these search algorithms is the notion of components or component decomposition. Cache was doing this, I think, and my CP2 compiler, they came out in the same year, were doing this notion. And I'm going to get to that, but let me just tell you one more thing about what happens here, which you have to do when you're doing this. In dealing with redundancy in this top-down compilation, a fundamental notion is that of formula caching, which means that if you look at part of your search, here's an example. I came down to this node by setting x1 to this, x2 to this. The formula simplified to this under this variable setting. Here's another part of the search space, different variable setting, but then I got the exact same formula. And I do not want to recompile in this case because I already compiled this guy. So what you do here is you basically cache your formula. You generate a key from it, cache it. And when you come to this point, say, I've seen this before, I don't want to do it again. So formula caching is very important, integral part of this game. And the last idea is the component cache, a component analysis. And the idea is in the process of fixing your values, you may disconnect your formula, right? And then what you want to do is spawn independent exhaustive DPLL searches. And that moves you up in terms of the class of circuits you can compile. So you have this guy here. and you set A to false. I had 4 clauses. I got 2 now, but they're actually disconnected. They don't share variables. You can compile these separately, or if you're doing exhaustive DPL, you run exhaustive DPL separately on each, and you get a trace from each, and you just conjoin these. And now, basically, I'm getting a trace which is weaker in terms of properties, and this will give you. Now you're going beyond FBD, you start getting deterministic decomposable negation form, actually even a specific class of those known as decision DNF, and I guess you get the idea of what's going on. So top-down compilation, that's the basic idea. There's all kind of bells and whistles. There are limitations in the sense that these will, in a sense, inherently generate deterministic circuits, because the essence of DPLL is you take a variable and say true, false, right? So you have established determinism, and even more specific type of determinism, which is we call decision determinism. I had a relatively recent paper with Umut Ostok. It's on the archive, which shows how you can go beyond that, but I'm gonna basically finish the story here. I have about a few minutes on explainable AI, just in terms of pointers, because, and that's what I'd like to end up with, and then we can probably have a discussion. And just before I do that part on explainable AI and tractable circuits, let me say that what we just saw, which is the notion of you take a search algorithm, keep a trace, you get a circuit, it has implications because it's a technique for proving lower bounds. That is, if you give me an algorithm X, and you can establish that it traces belong to this class of circuits, then that has implications. One, your algorithm X will explode on any formula that we know does not have a polysize representation in that circuit, in that class. Second, if we know that this circuit type allows certain operations to be in polytime, then your algorithm can do that as well. So I can infer positive things and negative things about your algorithm by establishing the class of tractable circuits that it traces generate. Okay, and in fact, there was work, I believe Paul was apparently here. He did show some lower bounds based on that. Okay. What I'd like to end is with a couple of remarks on explainable AI. This is something that I've been doing a lot of work over the last couple of years, and the basic idea is this. So I'm just going to give you the high-level intuition and how does work on explainable AI tie to what we talked about. It's pretty intriguing. Just the big picture and a couple of pointers, and we'll leave it at that. A lot of what's happening in AI today is basically this picture where you have data, and you learn a machine learning system based on this data. It could be Bayesian network classifier, neural network classifier, random forest. But these guys, classifiers are just functions. They map instances to decisions. And people now are interested in answering questions about these boxes. A long time ago, we used to build these boxes in a more maybe model-based fashion. So I can tell what they're doing. But now I label data, I get a box. It's not as easy to figure out what they're doing. People want to know, why did they make certain decisions? Are they robust enough? Prove formal properties? Do they make biased decisions, and so on? And the main observation here is that even though these boxes are numeric, and even though they're learned from data, the input-output are typically discrete. So they're just fancy representations of discrete functions. So the idea is we want to compile these ML systems, their input-output behavior, which is discrete, into a tractable circuit that captures that input-output behavior, and then I can actually then do the analysis on these tractable circuits. Of course, this is what I'm doing. There's the area now, mostly verification of neural networks. That's something similar, not necessarily by compiling into tractable circuits, but using other tools, directly SAT solvers, SMTs. The underlying idea is abstraction. Input-output behavior is not numeric. I can abstract that, and I can do various things. I usually use this example because it's very simple, about a naive-based classifier, as to give people a concrete image of what I just talked about. This is the features. I'm trying to find whether someone is pregnant or not. It's numeric. It was learned from data, but it does specify a discrete function. The inputs values of tests, discrete variables, decision is yes, no. I can use, for example, a decision diagram, an OBDD to represent this guy. In fact, this OBDD does match this classifier, guaranteed for any input output, whether you use the simple procedure on the OBDD or whether you assert this as evidence, compute probability, check against threshold, guaranteed you're going to get the same answer in both cases. So you can use this to do actually your reasoning. This picture opens up three questions. One is, what MLL systems I can compile? What tractable circuits, which you can guess, you choose the tractable circuit depending on what kind of queries you're interested in. But it also opened up a new path in the sense of what queries are interesting. So if you look at the traditional knowledge compilation map and the work, the classic queries, I want to conjoin, I want to disjoin, model counting. Now, when you start doing analysis of behavior, you come up with new queries that have to do with explanation, with robustness, and it's not as obvious of how to formulate these. So I give you the world in depth of computation. I think you can do anything for free, but get me the right answer. And you don't know, what's the right answer? So that opens up another dimension. And the line of work over the last couple of years have been looking at this. As far as compiling classifiers, Bayesian networks, this original work, the example I showed you about the naive Bayes, actually it's from a long time ago. When we did this, nobody was paying attention. Recently, we made this work for arbitrary Bayesian networks, at least in terms of formalization, and very limited types of binarized neural networks, and random forest can be compiled. Conceptually, these are the easiest because they're already actually almost symbolic. These are the hardest conceptually because in both the neural networks and decision trees and random forest, what the input-output behavior is already feed-forward. There's nothing sophisticated going on in terms of going from the input to the output. In Bayesian networks, it's a completely different story. I give you a model to find out what output the model will compute given an input. There's very subtle things happening, but there's quite a bit of work. And in terms of, excuse me, what kind of things you can do in terms of questions, there's explaining decisions, there is quantifying robustness, verifying properties, and so on. So I don't have time to go over this here, but I just want to point to that.
There are questions from Sibylle in the chat. Does compilation into a tractable circuit also work for CNNs or weighted random forest or balanced random forest? Or you'll take that later and wrap up what you're doing now?
So as far, okay, let me do this. I just have a couple of more words and then sure. I'll get to this question. I'm done here.
Sure.
Because I only did this part very briefly and there's quite a bit of work. And I think Joao will be talking about explainability later and he'll tell you about the broader picture, which is great. But as far as doing the tractable circuit compilation, there is a recent development from last summer and an associated paper. So if someone wants to start somewhere, for this particular audience, I would recommend this paper. And this has to do with explainability and the notion of something called a reason circuit or the complete reason. So if you give me a classifier and you give me an instance, then there is a decision made on that classifier, right? So in this paper, we introduced the notion of the complete reason behind a decision and a corresponding reason circuit, which is a tractable representation of it. And that reason circuit or that complete reason is a very interesting Boolean formula that if you have it, you can do a lot of reasoning about the decision, why it was made, is it biased, not biased. So it's kind of give you the handle on the logic behind why that decision was made. And the interesting thing is for a certain class of classifiers, including OBDDs and decision DNNFs, you can get that reason circuit in linear time. If you give me an instance, and then you say, give me the reason circuit for the decision on that instance, I can extract it from the classifier in linear time. Here's a classifier as an OBDD, this is the reason circuit, and it happens to be monotone. So it cannot get any better. And you can use this reason circuit for all kinds of things, from answering why the decision was made, is it biased, and the paper is titled On the Reasons Behind Decisions. It was in ECI 2020. You'll find a whole section there in that paper about what can you do once you get your hand on the reason circuit. But just as a teaser, you can use it to evaluate counterfactual statements like the following. So Susan was admitted by a classifier. And then there's this even if because statement. Susan would still be admitted even if she did not have a high GPA because she passed the entrance exam and comes from a rich hometown. Pretty subtle statement. You'll see in that paper how a statement like this can be evaluated based on the reason circuit behind the decision. So I'll leave it at this. I did mention that I taught a course this fall. There's 35 hours of material on the subject, starting with some basics on Boolean logic and SAT solving and so on. It's all on YouTube. And you can get to it and other things from our YouTube channel. Just type UCLA Automated Reasoning Group. You're going to get this page. You're going to see this course. And up there, you're going to see software and publications and so on. So thank you. This is pretty much all I want to say. And it looks like I'm on time. So Jacob, let me start with the question you asked. So sorry, I had to leave it. So there's the question. Can you repeat it again, Jacob?
The question was, does compilation into a tractable circuit also work for CNNs? What about weighted random forests and balanced random forests?
Very good. No, so at least what we've done so far for the compilation, no, we only did for neural networks binary inputs and step activation functions. We did actually compile something that resembles CNNs, but where we basically looked at the binarized version, because some of the examples we reported on were related to recognizing digits and images black and white. And to get neural networks that have good accuracy, we basically had a kind of a binary version of CNN that we compiled. It's very baby steps there. When you use other methods, not compilation, you can definitely scale a lot better. For random forests, we only did majority voting. And that's kind of a really straightforward encoding, because as I said, the random forests are almost, they have numbers, but these numbers are used in a binary fashion. So you have a decision that says if X is greater than 3.7, that's a binary condition. X is greater. So you take your X and discretize it, and then you're in the discrete world. And the good thing is you don't even have to discretize. The learning algorithm did the discretization for you. So you're almost there. But again, there's more sophisticated encoding, especially folks that not just compile, but actually use more general tools. And I think Joao will probably talk about some of this when he comes up later. Hope this answers the question. Any other questions?
So Sibylle says thank you in the chat. So yes, and adds the comment that imbalanced random forest samples are drawn non-uniformly. Any other questions? People are free to unmute or ask in the chat.
So hi, could you just say a little bit more about the partitioned STD case? Because that's what you need to get this PP to the PP type problem efficiently. Is that correct?
Right. So you mean constrained STDs?
Oh, constrained STDs.
Yes. So what happens there is that result, and that's the paper. Let me get there.
Oh, okay. Oh, that's just the constrained one. Sorry.
Yes. So this is the paper with Umut Ustok, and you need a special type of V3s. Because as you know, to even define a PP to the PP problem, you need to split the variables into X and Y, right? Mm-hmm. And what the way the X and Y influence things is they constrain what kind of V3 you can use. You have to use a particular type of V3, not any V3. So a V3 in general is any binary tree as long as the leaves are in one-to-one correspondence with your variables. And as far as constructing an STD, any of them will work. But of course, some will lead to smaller or bigger STDs. But when you want to use it for PP to the PP for computing expectations, you would need the V3 to satisfy a constraint based on what you choose to be your X and Y variables.
Okay, thanks. Yes, sorry.
And the paper is, this is the paper, Ostock in KR 2016 has all of the details on this one.
Thanks. One
Sure.
other comment just on this terminology things with arithmetic circuits and SPNs and whether what's decomposable. In some ways, it would actually be better to have a terminology that's more like the NNF thing, where the specific restrictions are explicit, because of course arithmetic circuits have been around since Strawson in the 1960s, studied on the theory side, and as some product networks doesn't really name either doesn't reflect the restriction. So just we should come up with one name that everybody kind of agrees on.
I agree. And the only temporary solution I have for this, and when I teach, I tell people, because I get a lot of people who's really confused, and some of them are not just students, by the way, some of them are researchers. And I say, here's the guide, go by the properties. So yes, we have messed it up as far as naming the final creatures, and there was a lot of confusion, but the properties are very clear and the implications of the properties are very clear. So anytime someone tells you, I have a new creature, says, let's wait to see if it's new or not. What are the properties? And for now, but I agree with you completely, Paul, and starting with the term arithmetic circuit was not the greatest choice, but that's what happened. So. All right. Any other questions?
There is nothing in the chat. Let's see, people, let's see. Feel free to ask any questions or unmute and just speak your mind.
All right.
Since there,
yes.
Wait, so is there one more question coming? It just says one more in the chat. Oh, is there a general technique to show exponential separations between these forms?
They vary, but some of the more interesting ones, and Paul is an expert also on this, is communication complexity. In fact, there was a separation between decomposable and deterministic, and for a long time it was predicated on a complexity assumption, and then folks then used some results from communication complexity to actually show a hard separation there. It's a fledge of techniques, but some of the latest and sharp ones were based on what's known as communication complexity. And I think Paul did some of these as well.
Sibylle wants to ask a question. Let's see if I manage to unmute her. Oh, Sibylle, can you speak? I think you should. Okay, I can.
Okay, I was unmuted, but well, on my headphones I still was muted. So one question, maybe it's a trivial one. When you speak about knowledge compilation, so you have a CNF formula, then you do this exhaustive DPLL search, then you have this circuit or other kind of language, however you call it, but this is only for this specific formula, right?
Yes, you're just compiling that specific formula. And this is a good point to say something. So typically this is worthwhile when you then have a whole bunch of queries on that formula. So if you just want to compute the model count, that's not typically what people use this. Sometimes you want to compute a lot of model counts. So what is a lot of model counts? It's just one formula. It has one model count. It's the marginal counts. Say how many models have A through B false. And these marginal counts, there could be an exponential number of them. So when you do the compilation, then you use that compilation very efficiently to answer an exponential number of queries. And that's what happens in probabilistic reasoning. You're computing then marginals for different pieces of evidence. Everything becomes linear at that point. So, which is great.
Yes, just when I heard it the first time, obviously as well, it's a knowledge compiler. I can translate, but of course it doesn't work. Now, obviously it's clear, but in the beginning it was just a bit misleading. But if I now, I do exhaustive DPLL or CDCL or whatever search, and I can create some DNF with disjoint cubes, then I could also call this a knowledge compiler. I don't record this search tree, but just this DNF.
Right. I mean, the search algorithm with a trace is what we call a knowledge compiler because it's rewriting your input.
Okay, thanks.
Sure.
Antonina had a question in the chat. For which of these do we know the complexity of computing or approximating minimum size? Which of these formulas?
Okay. Okay, maybe I'm not the best person. The complexity of compilation, Pierre Marquis would probably be. So OBDD, I guess I don't know that we've added much to what's known. This has been discussed for a very long time. It has not been a focus for me, frankly. Nothing immediately come up as far as this is compilability, right? This is the complexity of really doing the compilation process itself. I mean, you're lower bounded, but by what you can do after you got the circuit, but this is not something that I personally have investigated much.
So Armin is writing, these are all Boolean decision diagrams. Is there room for algebraic decision diagrams or even moment diagrams?
So, all right, so Boolean discrete, and there is the probabilistic versions. Now, you can, right? So if you look at what happened with OBDDs and how people generalize them and so on, that's quite a bit, actually, people did that. So let me just, I'm glad I'm on this particular slide now. This is a snapshot. There is a lot more than what I talked about. And in France in particular, there's a lot of variations, and it may include some of what Armin is asking about, I think, in the group in Toulouse. So there's a lot more. I gave you just a flavor of maybe some of the salient circuit types, but when you talk about what people now say knowledge compilation map, there were so many extensions and many more circuit types that were studied. And yeah, this is just really subset of it, and in particular, you know, mostly what I've introduced or worked closely on. The interesting thing about the notion of a knowledge compilation map is beyond the initial, at least the original one, beyond the set of circuits that it analyzed, is the methodology, right? So the fact that before that, there was no, you were not kind of expected to answer that many questions when you were to introduce a new creature and say, I'm going to compile into this. After the knowledge compilation map, it established a norm of that you have to tell me something about its succinctness. You have to tell me what is now possible in polytime if I compile into this guy. And can you tell me something about succinctness? And then after that, people start doing actually these reporting the results in this form. You tie to what exists by talking about relative succinctness to the extent that you can, what is enabled by it, which was interesting. So, but again, there's a lot more going on than what I portrayed today.
Okay, thank you so much, Adnan. So I'm, giving
thank you, everyone.
Applause on behalf of everybody.
Very good, very good. Thank you, guys, and it was a pleasure to participate today.
Okay. Thanks a lot.
Bye-bye.